Good afternoon, class. How is everyone today? Any questions before we move on? Yeah.
I have a question about antenna arrays.
Yeah, sure. Antenna arrays.
Good. If you widen an antenna aperture, it narrows the aim. Does the same work for arrays?
Absolutely. This is a great question. The question was, okay, so you have an antenna array, which is a bunch of little elements that by themselves are typically broadcast type antennas, omnidirectional. They don't have a lot of directivity. But when you add them together and put them in an array, whether it's a linear array, a bunch of ones placed in a line in one direction, or it could have a 2D array. And there are even 3D arrays. We had a PhD student do a dissertation topic on 3D arrays a couple years ago up on the 5th floor. William Barrett. Really neat satellite tracking array. And the idea behind an array is really the same as the dish antenna. I'm increasing the area over which I can absorb energy, and therefore I can also make the thing more directive. And it follows some of the same rules of thumb we learned about last time. For example, if you have an array that's this big, then your electromagnetic aperture is approximately that large. And you can put it in some of the gain formula, those rules of thumb formulas that we came up with last time. 30,000 divided by the 2 half-power beam widths is roughly going to be equal to that peak linear gain. And that's basically what you strive for. Now, what is the advantage of using an electrical array over a dish antenna? Dishes have to be mechanically pointed, right? You always know where the peak gain is. They're very simple. You have one feed antenna. We'll talk about this in a second. And one dish, and you just kind of rotate the whole assembly so that it points in the direction of reception. Arrays give you the ability to effectively move it electronically, which is nice because there's no latency involved. You don't have to wait for the giant dish assembly to sweep over here. You just change the phases of your elements along that array. Different phases will actually move the peak gain. But peak gain will be roughly the same, but it'll move into a different direction. And since it can be done electronically, you're talking about the ability to switch on the millisecond or even shorter time frames. Very nice. Now, what's the downside of that? The downside is that you must have, in order to change phases properly, you must have a coherent receiver chain on each and every element in your array. So think about that. 10 elements across by 10 elements down, that's a 100-element array. That'll give you a really nice programmable beam that can be placed on a satellite target. But you got to have 100 RF radio chains. That's 100 preamplifiers, 100 other chains to bring it down, to mix it down, and coherently combine them and phase them together. And that gets really prohibitive. It's possible, but only in certain applications. You could probably never justify doing this for like consumer electronics. But there's one application there's a couple applications that it is actually very beneficial. Yeah, Grant, you have a question?
Only for the AES arrays, not the PES arrays, one transmitter receiver module, and then it goes through line time changes to phase shift, and then combines it all, and then goes into the receiver end. So you have one TR module rather than multiple TR modules.
That's right. There are ways to control the actual phases, so that basically what Grant is saying is that you have a whole bunch of antennas. Let's say this is your array. And of course, if this was just one big dish, you could just put it into one receiver chain. Now, I said you could actually take these, and if you did 4 receiver chains, and we'll talk about this a little bit more in detail later, but basically when you do put 4 coherent receiver chains on here, you can get the amplitude and the phase out of the waves on these things. And really, it's the phase that's where all the interesting information is happening anyway. If these are phased correctly and identically, in other words, when these are combined into an adder, if this antenna experiences the same phase change through this RF chain before it is added it up together, and this one experiences the exact same electrical length, and this experiences the exact same electrical length, and etc., then the wave that hits this that has a uniform phase taper across the array is the one that gets the highest gain, because that's the one that has all the components that adds constructively, in the phasor domain. If you think of this as I and Q, the real part and imaginary part, in phase and quadrature. Well, you'll see this again later in the class. This component will have some sort of phase associated with it, and if this one is at the same phase, you'll get a little bit more, and a little bit more, and a little bit more, and then you'll get this perfect constructive addition. If it's coming in from the side, then you sort of get this, kink in it, and you wind up that the resultant isn't that far away from the origin. So that's where you're getting the gain. And so you can either change the phase lengths on these chains, or you can have a variable amplitude and phase way of combining these electronically. Now, William, you were talking, the type of system that you're talking about is where you switch in extra delays in these.
Well, there's the delay and then there's the Ferrite phase shift, right?
Yeah, so there are a couple different ways. You can actually switch in physical length on here. And in other situations, you can also, there are these things called ferrites, basically magnetic material that you can electronically control and retard the propagation velocity through the medium. So even though the physical length doesn't change through here, you could add one of these ferrites, and with a DC signal, you can make it so that it propagates slower or faster by biasing that. And that will effectively introduce a new phase. And if you did that, say, uniformly, you say, oh, I'm going to make it so that there's an extra 45 degrees of phase on this one, an extra 90 on this one, and an extra 135 degrees from this one. Well, depending on the spacing of this array, this is going to respond best to a wave coming from this direction. We know that there's exp to the minus jk distance phase taper as this thing moves through space. So as this thing washes across the array, in this particular direction, we'll call this 0 degrees. It'll be added with 135 degrees. The wave will drop a little bit more. And over here, it will have, say, negative 45 degrees. And I probably should have reversed the polarity here to make this work out. Let's make these negative. So this is negative 135. Negative 45 degrees later in the wave. At the same time, this is going down through experiencing an extra negative 90 degrees shift. That's also negative 135 degrees. Then you go a little bit further down. This is a negative 90 degrees phase. Negative 135 total. And then finally over here, you got negative 135. No extra phase shift on this one. Goes through and adds up. And that wave from the side is now coherently adding and giving you the peak gain. So that depends. It can be a little bit cheaper than doing individual receiver chains where you basically measure amplitude and phase here, amplitude and phase here, amplitude and phase here, amplitude and phase here, and then do all this synthesis in software. You put it into an FPGA that does your calculations, or one of those DSPs that are really fancy, and do all your pattern synthesis in software. And the primary drawback of doing it with with switch components, one is that it only gives you certain if you're not using the ferrite-based phase shifter, you only have sort of discrete settings that you can change your phase to. It doesn't give you that continuous ability to dial in different phases. The ferrites are usually continuous. The only problem with them is that they tend not to fizzle out at higher frequencies. They work best in like UHF, and they get dicier as you go up into the microwave frequency. Dicier and more expensive. So what we would really like, in order to do this really well, what we would like is to have 4 independent chains for this 4 antenna element array, and actually measure everything through those 4 chains, and then combine them based on that measurement, which is a very expensive setup. The other thing about ferrites, too, I should mention, is that they can be kind of lossy. And one of the things that we're going to learn by the end of this lecture is that even adding a little bit of loss at the very front end of your receiver can be catastrophic later on because you can never get it back. That's the part that you take the most care of when you design an RF receiver, the front part. So, yep, this is a, but otherwise than that, it works the same way as a dish antenna. I got this much area. I get a really nice narrow beam. I can just steer it electrically. It's interesting, there are some applications that you can actually justify the expense here, partly because nowadays we can actually make some RF electronics that are relatively cheap. It's amazing how far down it has come in price. I remember back in 2002, I took my first trip on JetBlue. Has anybody ever rode on that carrier? I think they don't have a hub in Atlanta, but sometimes you can find some cheap fares from other city to another city. And one of their business cases for establishing a new airline was they said, well, you know, we're going to be a budget service, but we're also going to offer our customers free satellite TV while they roam the country. And of course, how do you do that? Because the satellites are geostationary, but the plane is not. And so what they actually did, they contracted this through a company here in Atlanta, EMS. I don't know if you're familiar with any of them, but it's an outfit in North Atlanta. And they actually designed this 120-element phased array system to actually track the satellite electronically while you're in flight. And so if you ever look at one of the JetBlue planes, or even like Frontier, there are a couple other airlines that license this for a fee. You'd always know they're licensing it because you got to swipe the card on those airlines before, but you don't have to do it for JetBlue. At least you didn't used to. Now it's like you got to swipe your card for the peanuts. So I don't know. It's been a while since I've ridden some of these carriers. So yeah, there's like this 120-element array on the top of the antenna, or on the top of the fuselage, and you see that kind of flat, aerodynamically smooth radome. You can't see underneath of it, but it's basically this tilting array. So there's a little bit of mechanical tilt, and then there's some electrical tilting of the 120-element arrays. And there's actually, on each element, there's a little RF low noise amplifier on each and every one of those. Something that would have been cost prohibitive 10 years ago, but is now starting to come into play. So there's probably a lot you can do with array antennas. Some of you may, if you stay in the satellite field, you can work in those areas. Because at the end of the day, I always try to convince my friends this. In the end of the day, it may be expensive now, but in the long term, solid state electronics arrays always beat out these mechanical systems. It may take another couple decades to catch up with satellites, but I imagine in the not too distant future, you'll just put a fat panel out there in your yard, and you'll be able to get all sorts of dish TV, direct TV, maybe some other services on a satellite, internet, all through one conduit. It's a tricky and expensive problem in today's world, but it keeps getting cheaper every day. Oh yeah,
how do we actually sense the direction of the arrival of that plane there? Because then only you start steering it, right? But first of all, you need to sense it at which direction it's going. So how do you do it?
Yeah, so how do you do beams? How do you do direction of arrival estimates on a system like this? Well, there are a whole bunch of different algorithms. You could teach a course on how to do array steering and trying to figure out directions of arrival. One of the benefits of having 3 separate RX chains that are basically measuring the amplitude and phases individually before combining it, it's expensive to do, but once you have that, you can basically combine in software and say, oh, you know, what's the combination of phases that I have to add before they coherently add in one direction and give me my maximum component? Well, it looks like neg 45, neg 90, neg 135. That probably means that there's something coming from this direction over here. And that's a fairly straightforward problem. That's easy to do computationally. When you start to get into multipath, and you start to get, in satellite, even if you don't have multipath, maybe there's one satellite over here and another one over here, and they're both using the same channel. They're both broadcasting on the same frequency. Well, in a normal dish, you would be able to steer that. You just kind of sweep the dish, and you'd see a spike wherever the one over here is raining down at signal, and a spike over here where you see this received signal coming in. But of course, you have an array, and you just have numbers coming in, right? Amplitudes and phases. And then there's this issue of, well, you know, how do I there are algorithms for direction finding in those kind of environments where it will actually pick out multiple targets within your field of view. The only criterion is that you can't have more targets than array elements. Otherwise, you don't have enough degrees of freedom to do your steering. So you would like to have many more elements than you actually do signals raining down onto your antenna. I don't know what class that would. They do a little bit of array talk, theory and design and synthesis in the electromagnetic antennas class. There's a graduate level antennas class, and I believe that is in the spring. That's offered in the spring.
What you're describing is array signal processing.
That's right, and they talk a little bit about arrays and combining and stuff. The array signal processing, I think we also offer a class in that as well.
That's right.
Oh, okay. So what a great spring you could have. You could take the array signal processing and the EM antennas class that covers arrays and our stuff much more in detail. And you could be like the world's guru on antennas by the end of spring. I don't see a great deal of enthusiasm. Now, antennas are very fun. And there's always, there's never going to be any less wireless stuff than there is now. It's always getting more, right? So it's a good skill to have. So, boy, what question got us on this tangent? Did that answer any of the questions? Okay, good. Let's try to talk about interesting things, and sometimes I get sidetracked. So yeah, we were talking about antennas, and last time I basically taught you how to calculate the focus of a paraboloid. And that's usually on the next homework assignment, not next week, but the next one I offer. Usually I'll throw a dish in the hallway, or I used to let people go out on the roof, but now they lock the roof on Van Leer. And you got to take your tape measure and figure out where the focus is based on the geometry here. Remember, this was y is equal to x squared over 4p parabola. P is the distance between the focus and the center of the dish. Now, one of the tricky things is you got to make sure it's a symmetrical paraboloid dish. Oh, yeah, they're all over here. I'll darken this up. They were all hiding in the corner. So yeah, this is the distance p from here, and this is where you would put your feed element. And then you could have a coax or a waveguide that routes it on the back of your dish and then back down to your receiver unit here. So you can do a simple curve fit if you just measure a couple points, depth. You can then figure out where the focus is. If you ever get a chance, it's not necessarily allowed, but every once in a while, a door will be open and you can sneak out. There's actually a feedless dish out on the deck on the 5th floor of a Van Leer. If you can ever get out onto the roof, it's kind of fun to find the focus. It's the one where you basically get your buddy to go on the other side of the roof and just talk in a normal voice, and you just put your ear around, and if you find the focus, all of a sudden, it'll come in really clear. Why? Because guess what? It's the Helmholtz wave equation for acoustics, too. That describes the pressure waves that go through sound, go through the air when you make a noise. So anyway, this is the geometry that we're dealing with. And as I said, you have to be careful that it's actually a symmetrical paraboloid, because it is actually possible to just take a section of this that isn't symmetrical. So for example, if I take this part here, and I just use this shape here, well, any wave that comes in from our top side direction, basically negative y direction, will come in and have that great property still that if you trace the rays, the direction of propagation of the reflection off the surface here to the feed point, it will all collapse onto the feed point with the same distance traveled on each of these paths so that the phase will remain coherent and add constructively at that feed. Now just the feed is over here. There's maybe like a little armature and a cable that goes over here. What would be the advantage of using that kind of offset fed dish instead of the symmetrical paraboloid? It's smaller. That can be an advantage. We know in this class that smaller antennas mean smaller gain. But at the same time, you know, mechanical, if you've met your spec from the RF link, mechanically speaking, smaller is better. What else could be beneficial for doing that? An offset fed dish. Can anybody think of another benefit? Do I need to start bringing coffee to class? Yeah. I got mine before coffee. Oh, let's take this thought a little bit further. This is an excellent thought. Nathan made the comment that it looks cooler because now that there's not a blockage in front of the dish, you can see the dish DirecTV logo better. And you are right, in more ways than you could possibly guess. If you can block optics, you can block RF, right? This thing, if we were using a center-fed paraboloid, we'd have this armature and this feed element that was radiating in here, collecting energy if it was acting as a receiver. And of course, this shadows the dish. And, you know, it's not that big of a deal because it's only disturbing a little bit of the aperture, you know, a fraction of the aperture, but it will actually lower the efficiency of the dish.
And that's why they made the Cassegrain antenna with the hole and it just reflect off that to feed the dish?
Partly. We're going to talk about Cassegrains in 2 more lines of notes. Hold that thought. So yeah, this is an offset fed dish, and most of the DirecTV satellite dishes that you see are offset fed for that very reason. They don't want this to block any of this, so they get a nice clean aperture, reduce your aperture losses. And it looks cool. So some other alternatives that you will see out there. Let's say this is a cross-section of a paraboloid. And this is called the main reflector. And then you can also put a convex subreflector. And so here comes the plane wave. I'm tracing its directions of propagation. These will all reflect, and normally the focus would be right here, right? They want to collapse on that focus, but they hit this other subreflector, which is designed in such a way to collapse it down to this part of the dish. And what you do is you cut a hole in the back of this dish and you put like an open waveguide or a little horn antenna. And you can absorb the energy at that point instead of the feed there. And this is called what, William? Oh, yeah. Good job. A Cassegrain. And William said one of the benefits of this is that now you've got a little thing in the middle, but you don't have an armature kind of blocking view. So you take a little bit of blockage here, but you know this is like this is also a solid of revolution. So it's only chunking out just a small portion of your center of the dish. And it turns out most of your directivity comes from these side regions. So that's good. That's one of the benefits. What's another benefit? Anybody think of another one? Well, yeah, you can put all your electronics here. This is really good for high frequencies. Really good for high frequencies. Why? Well, compare this to what you got to do if you've got a conventional reflector. Wave comes in, collapses to a feed element here. You've got to have some sort of coaxial cable that runs this down and behind and then to your receiver electronics. The problem is we know that satellite communications can happen at 10, 20, 30, 40 gigahertz or even higher. And the problem is coax is lousy at those frequencies. You either have to get extremely expensive coax that isn't all that flexible, or what you would like to do, I mean, if you could, just go straight into waveguide. Because waveguide is much less lossy at those higher microwave frequencies. You can go down here. I mean, some coax, we were just measuring some in my 3425 class for demonstration earlier this morning. And, we were getting like, a couple dB per foot of loss at about 8 gigs. And it goes up exponentially from there on out. So if you're above 10 gigs, you don't want to use coax. Again, you're killing your signal at the most critical point when it's the weakest, as we're going to see in a second. So the nice thing about the Cassegrain is you can cut a hole in the back and you put that horn antenna, you're already at waveguide. And you can even just put your electronics right there. You don't have to port your signal very far before you can down convert it to a lower frequency, and then you can run as 5 miles on coax and you're fine. Maybe not quite that long, but when you get down below microwave frequencies, you can use a lot of coax and you don't get any signal loss over most reasonable distances. Now, an alternative to this would be the Gregorian dish. No, it was not named after me. I haven't done anything this cool. This, too, is like the Cassegrain in that it reflects the signal down to that same point and has some of the same benefits. The only difference is that this is a concave subreflector. And I guess the difference between these two, it's what mood you're in when you're fabbing or hammering out the metal. So sometimes you'll see convexes or concaves. It's the same thing. They just change the shape of this so that they can use it in a concave configuration. Because if this was pointed closer to the sky, higher up in altitude, this is convex, so it wouldn't collect water. That might be one of the benefits. This is actually one of the problems that we have with the Cassegrain up on the roof. Professor Steffes' group operates one up there. And if usually you put a little waveguide there, a little feed horn, there's a little plastic covering over there. And if the seal breaks on it, this thing has been pointing up for a while. Maybe people haven't turned it on in a few months. You go out and unscrew the low noise converter, and all this water falls out. Because the water collects in here, runs in, it'll seep into here, and then fill up this waveguide. Turns out that's a lousy thing to do to a waveguide. It stops working when you put water in it. So those are our 3 basic antenna types. The straight-up paraboloid with a single main reflector, and Gregorian, Cassegrain, the 2 different kinds of subreflectors. Any questions so far? No? Now, what are the sources of inefficiency in an dish antenna? Let's just mark down a few. So, on your homework, when you went to calculate the gain of your dish antennas that were used in that repeater link, you probably used gain is equal to 4 pi electromagnetic aperture over lambda squared. Now, truth be told, this is a nice rule of thumb, back of the envelope formula. Area electromagnetic for a dish, a nice round dish, would be pi r squared. Now, technically, not all of that energy makes it into the dish and up to the feed point. There are a couple of non-idealities that will lower the efficiency of this. So there's actually this efficiency term. We often use eta for every blanket efficiency. A number between 0 and 1. And 80% winds up being a really nice ballpark. If you've gotten your dish up to 80%, it's usually a pretty good dish. Yeah, Alex?
Where are you pulling your notation from? Wiki prefers mu.
I have always used it as eta in all of my textbooks. Yeah, I think eta is more pure EM theory community, and I would guess mu is more maybe, I don't know, GTRI community? I don't know. What book does that come from?
I'll look into it.
Oh, okay.
It was just curiosity.
I always used to joke, there are probably 4,000 electromagnetics professors in the United States, which means there are 4,000 different notations for everything that we learn out there. So eta, in some books, mu. Still the same. It's just they'll be calling it dish efficiency or antenna efficiency, and it is actually the multiplication, because there's a lot of stuff going on in a dish antenna. It winds up being the multiplication of a whole bunch of efficiency factors. For example, one of the things you have to worry about is polarization efficiency. That is, okay, let's say I want to transmit linear polarization. We talked a little bit about polarization. That's the direction that the E field propagates in when you are receiving or transmitting a wave. Let's say I'm using my dish as a transmitter. I put a half-wave dipole in the feed element. And it's radiating in all directions. It'll illuminate that dish. And it's got vertical polarization. But it's a curved surface. And so the wave that reflects off of that, I mean, we can think of a dish as basically a spherical to plane wave converter. That's really what it is. Taking a spherical wave and flattening out the phase front so that it can propagate as one collimated beam, which will then spread out according to the wave equation. But you'll get a nice pattern in the peak direction. So it's going to reflect off there, and the polarization, especially on the fringe diagonals of the dish, it's going to skew a little bit. So not 100% of your energy is going to make it to linear polarization. There'll be some cross-pole illumination of that dish. And if that's the case, a typical value, I have some typical values here. Polarization loss, that's usually pretty good. We can maybe get this 98% efficient. This is just a representative value. And then there's also illumination efficiency. Now, illumination efficiency, a typical value for that might be like 98% again. And what does that mean? Well, the example that I just talked about. Let's say I have a half-wave dipole or a small Hertzian dipole as my feed element. It's illuminating the dish. Why is that actually a lousy antenna to use at your feed? It'll work, but this will be way lower than 98%.
You're wasting most of your energy radiating in the wrong direction.
That's right. As a transmitter, if I were transmitting it out, that dish would only collect a portion of that omnidirectional radiator. And of course, reciprocity theorem says even though this is a much more complicated system, transmit gain is going to be equal to receive gain. It's a crappy transmitter. It's an inefficient radiator. You'll lose several dB at least in that scenario of what your peak gain could have been. And so what you'd like to do is put like a horn or or a patch antenna, or sometimes if you want to do circular polarization, you like wind a couple of rings for an elliptical antenna. That's a way to transmit circular polarization. You put that in your feed element, and make sure an antenna like that has a beam width of 90 degrees, something like that. Remember, ideally what we would like is a sector feed element, something that illuminates the entire dish and then goes to 0 as soon as it hits to the edge. But why is this impossible to make? What would my antenna have to look like in order to have a perfect null like that? Nice uniform illumination, complete, dies off, 0 radiation everywhere else in space.
You have to connect it to the dish.
Well, you
get back lobes and side lobes, but if you connected it directly to the dish, you kind of do that.
Well, conceivably, that's a good point. We'll talk about that in a second. That's spillover, dish spillover. Oh, yeah, Kamal, that's great. Wow, Kamal, your 3065 instructor must have been something else.
It's pretty good.
It's like, your 3065 instructor is totally reusing some lecture material, isn't he? No, Kamal is right. It would have to be an infinitely large antenna to get that pattern. Why is that? Remember, the pattern is a Fourier transform of the current distribution, or the field distribution, however which way you want to work. If I have a perfect pattern like this, basically a sector, if I unwrap that from polar coordinates and think of that as just a function, it's kind of like a box function, right? The Fourier transform of what is a box? A sink. When does a sink go to 0? Never. It periodically crosses 0, but you would have to have an infinitely large antenna to make a perfectly sharp pattern like that. So this is like 90% of pattern synthesis. You could spend weeks and weeks studying it, but we can all crystallize it down to this. How do you get that really nice pattern with as small of an antenna as possible? You could spend many, many weeks studying that problem. There are some people that have spent a lifetime studying that problem. And so invariably, no matter how good you do, you will always have sort of you won't have that sharp radiation pattern. It'll fall off quickly, hopefully, but never perfectly, so that you'll be skimping a little bit on irradiating the edge here. And you're also going to spill some stuff over. And of course, that causes a problem, main reflector spillover. Not only did I not illuminate this 100%, but I'm spilling over from my main reflector. And now I'll start to get some stuff that diffracts around the corner. And that has main reflector spillover efficiency. Let's say that's 96%. So you can design it pretty well. And of course, I also get spillovers if I have a subreflector here too, right? Just because I used a Cassegrain or a Gregorian antenna doesn't mean that I've solved this problem. In fact, that just adds another subreflector efficiency, which is typically like 88%. Blockage losses, even if I do an offset feed antenna, there'll still be some blockages on the side coming in. But if I do a center fed, I'll have more blockages. If I have a Cassegrain or a Gregorian, I'll minimize some of the blockages due to the armature. But I will have still that center that's taken a chunk out. And so blockage losses. A reasonable assumption for blockage losses is about 93%. Phase and surface errors. A typical value for that is 92%. Lose about 8%. Just due to the fact that maybe your phase is not perfectly parabolic. There are going to be some machining errors. Large-scale sort of machining errors in your dish are called aberrations. And smaller scale errors, like if you look at it a little bit closer, surface roughness is what dominates the phase errors in that case. So one way, do you know how they check for aberrations in dishes?
Optically.
Optically, yeah. What do they do? How do they do that?
First, they put little reflective dots on this mesh, took a photograph of it. The computer would actually analyze it and say where they needed to adjust some pull chains that held it together.
Oh, interesting. Interesting. Yeah, I'm familiar with the much less low-tech solution.
Just look at it and see.
You put a light bulb at the focal point, you screw it in, and then you go across the room and you look at it, and if you don't see uniform illumination in your dish, you screwed it up. But you can use the computer and do something really sophisticated too. So remember, dishes work at optical frequencies. If they basically spray paint a bunch of silvering material on it to kind of make it highly reflective. And then when they light up the light bulb in the center, you should see nice uniform illumination. If there's kind of a dark patch, then you know you have an aberration in your otherwise what should be a perfectly parabolic dish antenna. So that's at large scale. And you definitely want to get that part right. Now, dish antennas, what limits their frequency use? What determines the lowest possible frequency you can use a dish antenna? Well, pretty much two things. Size, right? You need at least a couple wavelengths across to actually get this phasing effect. You also have to make sure that your feed element is broadband too, that it works down to that frequency. So those two things are the things you look for when you spec out an antenna. Now, your size looks good. What determines on the high end, the highest frequency you can possibly use? Let's assume that we've got an antenna that can support, a feed antenna that can support a really high frequency. What is likely going to do your dish in? Well, it's usually these phase errors, particularly in the form of surface roughness. Like, as you get smaller and smaller in the wavelength, higher in frequency, that surface doesn't change physically, but electromagnetically it gets rougher. Everything scales with respect to wavelength in electromagnetics. So what we want to do, we want to check the roughness. You look at the dish, and maybe it'll have some wiggles in it. And as soon as the standard deviation of those wiggles exceeds 1/8 of a wavelength, this is standard deviation of surface roughness. As soon as that gets more than 1/8 of a wavelength, what happens is that you start to get a significant amount of non-specular diffuse scattering. In other words, a wave that strikes this, it will still produce an angle of incidence equal to angle of reflection type well-defined wave coming off there. But then it will also take some of that power and start scattering it in various directions away from your feed element. And of course, it's got to rob that power from the specular direction when it's doing that. So, you can actually use this to your advantage as a satellite dish designer. One of the biggest problems that they have in satellite dish design is that you have this big dish, and it's like a giant sail, right? And if a big wind comes, you can get a tremendous amount of torque on the base of that thing if you've got the dish pointed even close to the horizon. What's one of the ways around that? Well, we would like to perforate our dish. Just use a mesh, an electronic, a mesh. As long as the holes in that mesh are about 1/8 of a wavelength or smaller, it'll look like a solid conductor to the EM wave, but the wind will pass right through it. So I'm sure you've seen plenty of examples of that in real life. A lot of the commercial dishes that we used to use for 6 gigahertz downlinks, 4 gigahertz downlinks, were perforated mesh type antennas. Yeah. Did somebody have a question here?
Yeah, that was based off of standard deviation. What if the satellite was very rough, but consistently rough?
What if the satellite dish antenna was consistently rough, but consistently rough, like had maybe corrugation.
Right. So the standard deviation would be low, but it's still.
This is called the Rayleigh criterion for a rough surface, and it turns out that that's a really good question. This still holds in that scenario. This will still start robbing energy out of the specular direction and start scattering it. The only interesting thing about this is that because if it's a consistently periodic surface, you get something called Bragg scattering, which just means that, yeah, it's robbing energy from the specular direction, but it's sending out spectral components in consistent, discrete directions. So what you'll find is that you'll have a main wave coming out here, and then you'll have some constructive interference that occur at various discrete directions where, because of the symmetry of the problem, everything reinforces constructively in that direction. You can actually, and this is very interesting, there are some techniques out here now where you can make a reflector, and by adding some periodic surfaces to it and adjusting them electronically, like through some varactor diodes or some other transistor biasing, you can actually take a wave, get it to reflect off there, and then reflect it in different directions. And it's a very similar phenomenon. You're introducing a periodicity to the reflective surface, almost like it was an array. In fact, that's one of the ways you can model this situation. You think of this as a whole bunch of little array antennas that'll spit out a non-specular phasing and then a bunch of grating lobes in certain directions. And in doing so, it will, again, rob energy that's hitting the surface and should have been going towards the feed antenna. Rough surface scattering is a beautiful, beautiful problem. We almost cover none of it in the curriculum. Every once in a while, I get to teach this advanced EM class. I did it like 2 years ago, and we spent a couple weeks on rough surface scattering. The goal of the class is basically to get students to read the transactions of antennas and propagation with some confidence and not feel like, a 3-year-old, because it can get really intimidating when you read all those terminologies. But, it's just jargon. Even rocket science isn't rocket science when you're introduced to it, right? We're studying rocket science in this class. Did you feel intimidated? No. Okay. Actually, I saw this really cool antenna over at GTRI 5 or 6 years ago. They were studying a portable dish antenna that maybe a soldier or somebody in the field, an emergency worker could take out, and it was inflatable. It was a dish antenna. And so they basically would, you'd take it out of your pack and it would blow up, and when it was in an inflated position, it would be a paraboloid, and kind of look like this from the cross section. And they had a reflective material in here, and actually a very opaque material up here. This is plastic, so RF will go right through it. Why would you want this to be really opaque?
Heat would increase the volume of the air and distort the shape.
That is the non-catastrophic reason you would do it. So if light shines down on this, you could conceivably heat up the air and distort the shape. Not potentially. But if you have a feed element here, there are actually stories of this happening in real-life dish reflector antennas that were shiny. The sun comes in here, collapses its rays onto and you incinerate your feed element. That actually happens if you're not careful. It's just like the little kid with the magnifying glass and the ants. Admit it, the camera's not on you now. How many people did that when you were a kid? Yeah. Same problem in dish antenna design. So you can inflate a dish. This is a really nice way to make a light dish. And in fact, this is how some satellites actually do this in space. Satellites need dish antennas to communicate over very long distances to at least get some directionality in a synchronous Earth orbit, or if it's a deep space mission, you need a lot of directionality to boost the gain and the link margins for those hundreds of millions of kilometers you have to traverse. And so weight is everything in space. The lighter the load, the better it performs, the cheaper the mission gets, because it gets extraordinarily expensive just by adding another pound to your spacecraft. And dishes are heavy. So one of the ways, and mechanically difficult to put in a payload bay of a rocket, right? You want a dish this big, it's going to be hard to fit that into your rocket. So one of the ways that they do this in space is they have like a soft dish material that when the satellite has been deployed and is on its merry way, it unfurls. And there are even like certain designs that people have experimented with where they'll like spray a foam on it so that it hardens, and then there'll be a little nozzle that sprays a conductive coating on it so that it turns into an electromagnetic reflector if it was just a really thin dielectric material. Yeah, Grant. I'm going to call you Grant this time.
Is the golden mesh. And first ones that Harris taking the course and goes, well, how do you get that stuff? And they go, well, we bought a pantyhose manufacturer and converted them to use gold thread. And so that's how the dishes work now. They have a gold mesh that has arms that hold it, and then little ropes that connect it to the arms. So when the arms fully extend, it makes a perfect dish, and yet it can collapse up. It's fine.
So gold mesh, just run it through the pantyhose dye machine, and you've got yourself a mesh that you can unfurl. That's a great idea. Why do you have to use gold?
It's more flexible.
Yeah. It's actually gold. Not many people realize gold has less bulk conductivity than copper. Slightly less in terms of Siemens per meter. But it's usually that malleability that everybody's always after. In the case of the mesh, yeah, you don't want the thing to tear open when you open the thing up.
Problem if you get a run in it.
Then you cannot use it for satellites or for hosiery. Yep. So anyway, we forgot to add all of our numbers up. If you multiply all these together, it's about 80%. That's where we got the 80% from. And dish antennas we can use that same formula that we talked about last time. And sort of the efficiency is folded into this formula already. This is already a rule of thumb, so changing it plus or minus 80%, 20% is not going to affect very much. But basically 30,000 divided by theta half power beam width, phi half power beam width is equal to linear gain. Every once in a while, a poor student gets confused and thinks that this is dBi. And they're like, I got a 300 dBi antenna. It's like, no, you didn't. That's bigger than the Earth. And in circular dishes, these are roughly the same. You get about the same beam width in one direction as you do the other because it's roughly radially symmetric. Okay, let me show you. I do have this one slide I got off the NRAO website. And I'll show it to you on the overhead here. And I promise not to press the wrong button this time like I did last time. And not this again. There it is. There it is. Great. It just takes a couple minutes to warm up. So has anybody seen this before in real life? Do you know what this is? Anyone? It's actually the world's largest dish antenna. It's in Green Bank, West Virginia. And it's quite a haul to get there. You have to take all these mountainous roads because it's used for radio astronomy, right? And the thing is, you don't want to go where there are other radio sources to do your radio astronomy. So like the middle of West Virginia seems like a great place. You got all these mountains surrounding you, and there's no civilization for miles. I mean, there's civilization in West Virginia, but there's not civilization anywhere near this antenna. I don't mean to make West Virginia jokes here, even though I am from Virginia Tech, and that is like one of our rivals. I had a poor kid from West Virginia, in West Virginia University, went there for undergrad, and he was in my Satcom class a couple of years ago. And pretty much after I showed this, there were pretty much nothing but West Virginia jokes for the rest of the class. But since this class is being taped, I'm not going to do that. So anyway, yep, here it is. This is actually the length of a football field. This is the coolest thing. That you can tour it for free. You can go and see the substation, and there's actually a small old radio telescope, like this really array of dipoles that was used 100 years ago to measure the cosmic background radiation. That was the first measurement of the cosmic background radiation. And it's actually on display there in the front of the lot. So they've got this dish, and they got a couple smaller ones too. And it's just fun. If you're an electrical engineer, it's a really fun place to visit. If you're anyone else, it's probably dull as anything. But it's a beautiful drive to get up there. So I encourage you to do that. And I think it's free. You can just hop on any tour. It's public relations from the NRAO. So you can see this thing, and this thing is wild. First of all, notice, again, offset fed. So actually the aperture, the plane wave would come down here in this configuration. And this is mechanically steerable in both theta and phi. So you can get full coverage of the sky. It's really amazing. And one of the interesting design aspects of this is that the dish is so large that depending on how it's tilted, you know, gravity is kind of pulling on it and deforming it in one direction. And in other configurations, it's pulling on it and deforming it in the other direction. So to counteract those aberrations on such a big dish, which are a big deal at the high frequencies, what they have is the subreflector, or the main reflector, is actually not a solid dish. It's a bunch of little facets that are laser actuated, and they can actually be tilted a little bit, back and forth, left and right, up and down, to compensate for the curvature of the dish as it turns and deforms under gravity. What a great double E problem that is. Optics, RF, controls, living together. So anyway, I just wanted to show you that. It's a good place to go visit. Okay, that was it. So speaking of cosmic thermal background radiation, are you ready to talk about noise? Anybody have any remaining dish antenna questions? No? Okay. Well, communications would be a snap if we didn't have the next phenomenon we're about to introduce. And that is thermal noise. There are different types of noise that you want to get out of your communication system. And if you could completely exclude noise from a communication system, you could transmit the entire Encyclopedia Britannica instantly at any given frequency, because you would have no ambiguity as to what the signal levels you could send would be. You could send 5 gajillion QAM symbols, and in just a couple symbols you'd transmit the whole thing, and you could detect it perfectly. You didn't have any uncertainty in the signal that you got into, that you received. So noise is a big deal, and it turns out that there are two types of noise, right? There's man-made noise, which we usually call interference, and then there's this natural noise that you can never get rid of. And when we're doing satellite communications, usually our dish, if we're using, say, geostationary satellites to communicate, our Earth station has done such a good job of pointing and spatially rejecting the other signals coming into the dish that thermal noise is sort of the limitation of how well your system can perform. This is different than a cellular network where, if you go and try to make a call on one of the networks here in Atlanta, you're probably more often than not interference limited not noise limited. Only when you get out to like Alpharetta or the suburbs do you run onto the edge of coverage, and then you start to become noise limited instead of interference limited. But noise is a big deal in satellite, especially on space links, because that tends to be our limiting factor in many links. So where does this come from? This phenomenon of thermal noise has to do with the black body radiation that many of you studied in undergrad in your thermodynamics course. You know, if you have any object that isn't at absolute zero, it's going to be radiating heat into the environment. As it gets hotter, it radiates more. And where does that radiation come from? Well, you know, anything that's not at absolute zero has atoms and molecules in it that are wiggling around. And all those wiggling modes are quantized, right? Sort of wiggling, rotating, vibrating on different bond levels, energy levels. Electrons are at higher or lower energy levels. That tends to be a higher energy transform. But these most atoms and molecules have these sort of vibrational and rotational modes that are lower energy. And when one of those modes loses energy or exchanges energy, there's a photon that goes off and carries energy away at some frequency that could be anywhere from close to DC all the way up to, you know, optical frequencies if necessary. Now, it would have to get really hot in order to see something optically. But of course, we have hot things all the time that we see optically, like the sun, right? It has lots of optical radiation because it's at an extraordinarily hot temperature. RF is much quieter, but there's always this background radiation coming from everywhere. Unless you could surround yourself with 0-degree Kelvin matter that was impervious to radiation, which obviously you can't do, you're always going to have a little bit of noise. In fact, even if you're in the blackest part of space, there will always be that 3 Kelvin background temperature. I think it's left over from the Big Bang or something. And it's always back there, providing just a little bit of background heat to totally ruin communications. And so that's the thing that we have to contend with. Now, when we bring our antennas down to Earth, things get warmer, right? We have a cold sky above, but sometimes the really hot sun goes through it. And if it passes in front of the lobe of your antenna, you start getting a whole bunch of radiation. And of course, the sky, the air molecules add some temperature of their own there, and our Earth is usually about 270 degrees Kelvin on average. It's a typical room temperature value. And the nice thing about kelvins, you know, that's the scale that we work with in black body radiation, the absolute temperature scale. And that doesn't change that much on Earth. I mean, you might think it does. You think, oh man, it's 30 degrees Fahrenheit here in the winter, and 100 degrees in the summer. But on the absolute Kelvin scale, that's relatively small. So 270 degrees, you probably use that value without any regard to what the season is for an average of room temperature. Now, the question is, if I have an antenna and I don't have any man-made transmitters in the band of this antenna, instead, I'm just going to observe the voltage coming out of that due to these random photons at all these different frequencies striking this from one moment to the next. What kind of signal comes out of here? If I could draw it on the board, what would that look like? Gaussian noise. Somebody said Gaussian noise. Because the answer is always Gaussian noise, right? There isn't anything that we can't approximate with a Gaussian, isn't there? White Gaussian noise. White Gaussian noise. Let's break that down, because those mean two different things, and we'll tell you what they mean in a second. White, Gaussian. Gaussian noise. Okay, I'm going to draw this voltage function of white Gaussian noise as a function of time. That's approximately white Gaussian noise. What does it mean more specifically? Well, and I did a lousy job of showing this, but the Gaussian part of this means that if we took this random process and observed many ensembles of it, or if we just took it if it was an ergodic process, and it is for the most part, if you looked at it over many different observations in time, what you would find is that at any given moment, the amplitude in terms of volts of this distribution would be unpredictable, but if you accumulated a histogram of them, you would get this nice zero mean Gaussian. Zero mean Gaussian histogram. With standard deviation sigma sub n. So you'll recall the PDF for a Gaussian that's zero mean and has a standard deviation of sigma sub n. Recall that the standard deviation is basically the interval at which 2/3 of the amplitudes would occur. 2 out of 3 times, if I picked a value at random, it would be zero mean plus or minus a standard deviation. And the PDF that would describe such a Gaussian would be exp to the minus amplitude squared over 2 sigma sub n squared divided by the square root of 2 pi times sigma sub n in the denominator. Noise standard deviation. So that's the Gaussian part of this. And the white, this describes the first order statistics, the amplitude distribution. The white part of this describes how this process evolves over time, the second order statistics of the random process. Now, the second order statistics, there are a couple different ways of that. Second order statistics are defined as how to relate one part of the process to the other. So a first order statistic for this would be like the mean. What's the mean of this signal? Oh, it would be 0. What's the mean squared? That's actually a very useful parameter. We write it as ensemble average of this noise process, quantity squared, and it would wind up being sigma n squared, the standard deviation. That tells you how much energy is in the process. As the thing grows in standard deviation, it has more energy in it. Okay, so that's a first order statistic. And keep in mind that there's always this confusion in stochastic processes and random process theory between the order of a process and the moment of a process. So the mean of this process is the first moment of the random variable v, or the random process v evaluated at a time. The second moment is what we did here. It's mean squared, the average of the squared value. We could raise this to the third, and that would be the third order moment. Excuse me, the third moment of the process. We raise it to the fourth, that would be the fourth moment of the process. Those are all still first order statistics because it only involves the histogram of observation at one point in the voltage. Now, when we go to the second order statistic, that's where the white comes in. If we look at how does this point relate to this point, one way to define that is through the correlation. If I know something about this point in space, can it tell me anything about this other point in space? And since most random processes that we encounter in real life, have some sort of curviness to them, right? If you know a little bit about this point, you can tell a little bit about this point over here. And what you can tell about this point over here drops off a little bit, then it drops off. And the more you spread out your observation point, the less you know about this one if you know this one. That makes sense, right? A white process is different. It's one of the only kind of processes where knowing what's going on here tells you nothing about what's going on immediately next to it. Every single sample that you pick out of just one measured waveform is completely uncorrelated with any other sample. And that actually has a really interesting spectral property. When you run that type of process through your spectrum analyzer, you basically take the Fourier transform and look at the power as a function of hertz. That mathematical property of complete decorrelation means that the magnitude squared of the Fourier transform is a flat line. Oh, this should be frequency. When you graph it with respect to frequency, it's completely flat. Completely flat. In fact, we give it a constant n naught over 2, where n naught is usually measured in watts per hertz. And this actually winds up being a really good model for thermal noise in the microwave band. If you go down to UHF, it's roughly the same watts per hertz in spectral density that if you go up to the higher microwave frequencies. And so over the bandwidth of a signal, if I transmit, say, a signal with bandwidth B, now, of course, if this is a pure mathematical Fourier transform, I should have the negative complex conjugate mirror image on this other side, which is also B. And if this is a band-limited signal, anything outside of that is going to be non-signal. So I can run this through a filter at some point in my detection algorithm. And what I should get is the superposition of my signal with bandwidth B and some residual noise inside. And so I can never get rid of this by pure filtering, this noise in here, because that's shared with information. If I get rid of that with conventional filtering, I'm getting rid of information. And therefore, when we define a system, when we go to calculate the system noise in a communication link, we basically want to get the n naught, that level of white noise in that band, n naught over 2, and we multiply it by the bandwidth of the system. And of course, there's 2 of them mathematically. So if we've represented it with this Gaussian white noise signal level, by mathematical convention, there should be 2 of them. So total noise power
is that the same as noise spectral density?
the n naught would be the noise spectral density. That's right, watts per hertz. It would be n naught B. And in fact, the environment that an antenna operates with, we often give it what's called the physical temperature to kind of tie it into the physics of the scenario. And this n naught is typically Boltzmann's constant times the physical temperature. So let me write these down. Bolt and physical temperature. Let me give you Boltzmann's constant so you can have it in your notes. K is equal to 1.39 times 10 to the negative 23 joules per Kelvin. Energy per temperature. And so our total noise formula can be written as Pn equals K physical temperature, Boltzmann's constant times physical temperature times bandwidth. A very useful formula to have. It provides a lot of physical intuition too. And you have to be careful with this physical temperature because there isn't a really easy way to calculate it. There are only kind of rules of thumb for different types of antennas. And you usually have to get it off of a table and kind of intuitively say, okay, that kind of makes sense. If I have an antenna that's pointing to the blackness of space, and the lobe is in space, and it's not seeing much of the rest of the Earth, and the physical temperature can get quite low, 30, 40 kelvins, 50 kelvins, 100 kelvins. This is a value that we could use depending on the situation. But if the sun comes and passes in front of it, that can jump to thousands of kelvins. And it could actually knock down your carrier to noise ratio by 2 orders of magnitude, 3 orders of magnitude. And then communication's done for a couple minutes until the sun moves out of the beam. If you're in a deep space link, it might even be lower than that. If you're a broadcast antenna on Earth, it's probably a good bit higher than that. It's probably 200, 250, 270 Kelvin, depending on where you're operating. But people like to describe physical temperatures and do that instead of N-naughts. N-naught tends to be used in the comm world for just doing analysis of communication system, but physical temperature tends to be used in RF texts and that sort of analysis. So this is how you convert between the two. Okay. And this is really nice because you can actually calculate a carrier to noise ratio now, right? Carrier to noise ratio or CNR is basically the received power, P sub r, to your noise power. And this is related to your signal to noise ratio, which is your signal power to your noise power when you've mixed it down to a lower frequency. We'll talk about that in a second. But we actually have enough to calculate this. We now know how to calculate noise power. That's KTB. Receive power, well, that you get from your link budget in a wireless link. And this probably is just about the single most important parameter to characterize in a communication link, because it tells you how bad it's going to be. Sometimes you'll see carrier to interference ratio, CIR. In that case, that usually implies that there's some man-made interference, so you could add that into the denominator. Or CINR, carrier to interference plus noise ratio. And they take the noise and the interference as well, lump them together and put that in the denominator. But it's all variations on basically the same idea. I have a desired signal, I have an undesired signal. As that ratio degrades, gets smaller, it's going to be harder to detect any information coming in on the carrier. So that's our number one parameter for our comm system. And as we're going to turn out, it's not going to be just the thermal noise that we have to worry about. This is basically the showstopper in terms of how high the carrier to noise ratio gets. As soon as your signal gets into your RF chain, this is going to degrade for other reasons as well. So let's talk about those. Actually, let's not talk about those. The bell is going to ring in like 5 seconds.